Hello everyone. We are starting to record a new lecture. This is the fifth lecture, lecture 5 of the course Neural Networks, Artificial Neural Networks and Neural Control. Today we are going to record Chapter 3. This is from the Hacking book. We are following this book. Hopefully from chapter 1 to chapter 6 we are going to cover everything. Single layer perceptron, this is the topic of this chapter. If you like, you could just view what is going on in this chapter, and you can read the material truly to this chapter 3, and this is introducing single layer perceptron. And of course the class notes would be from this file. Since in the previous edition of the book this was chapter 4, now this is chapter 3, perceptron, single layer perceptron. So let's define originally what is perceptron. Perceptron refers to perceptual nerve cell and is derived from the perception and perceptron. This is the definition. This statement is showing you the definition of what is perceptron and where is the root for this derivation. Rosenberg proved that if the input pattern were selected from two different groups of inputs, let's say we have two classes of inputs, so that the two classes could be linearly separated, then the perceptron algorithm would converge and the separation of the two classes would be performed by a single page. So as we said, like AND, OR, NAND, NOR, we have two classes of inputs. They can be linearly separated. Therefore, single layer perceptron can be converged and can solve the problem and can give a result and can classify these two classes of inputs into separate classes by a single page. Let's show how a single layer perceptron can be presented. The presentation of a single layer perceptron, as you could see, we have a single unit, single nerve, single cell. That this should be the input vector. As you could see, there are some variables x1, x2, x3 up to xp. This is called the input vector, input signal from each of these sensors, from each of these variables. You would have a input to the cell, and you do have the threshold, which would be referred as the bias, threshold theta, and the output is y. So we have only one output to this cell, and this can show you a single layer perceptron or single unit. This originally we called it, we did call this originally a basic model of neural network, McClatch-Pitts model. So it is better to show the signal flow graph for single layer perceptron. In this signal flow graph, we could show the input vector again and the weights related to each variable. For example, for variable x1, we have w1. This would be entered to the node, to the unit, to the cell, x1 w1, x2 with w2, and xp with wp. And in order to input the threshold, we can use a constant input with some -1, and the output of the cell should be Vj, and with respect to the nonlinear transfer function for this single layer perceptron, if you see, we have used the hard limiter Yj, which is the output of the perceptron, can be defined with respect to the transfer function. So as you could see, the transfer function of this perceptron is a symmetric hard limit transfer function. In this respect, the output could be -1 or +1. So the summation input times weights and the transfer function and the output transfer of this unit can be define can define the output for us. So first, how do we calculate Vj? So originally we have to find Vj. V equals to sigma Wixi minus theta, the summation of weights times inputs minus threshold. And with respect to the transfer function, we could say if Vj is positive, Yj is equals to 1. In this respect, if Vj is negative, Yj is -1. The duty of this cell is to divide the input signals into two classes, C1 and C2. So this single layer perceptron with respect to the hard limit transfer function can divide the input signals into two classes, C1 and C2. Therefore, if Yj is 1, then the vector input vector x belongs to class C1. And if Yj is -1, then x belongs to class C2. Very simply, you can see the representation of how a single layer perceptron can linearly separate the output signals into two classes, C1 and C2. With respect to this, you can see the illustration of linearly separable of two-dimensional two classes pattern classification problem. You see we have the input signals which are in class 1, the dark area, and class 2 in the light area. And this is the decision boundary, the surface that is dividing this area into two classes. All the inputs, all the patterns are the vectors in class 1 and in class 2 using this decision boundary. The decision boundary is a surface that is dividing the area into two classes, C1 and C2. With respect to this, the equation for this line would be W1x1 plus W2x2 minus theta, which is equals to 0. Therefore, let's write separation of these two classes is accomplished by a level with equation sigma Wixi minus theta equals to 0, which is giving you this decision boundary, which is giving you the equation of a straight line. This is the equation of a straight line dividing the area into two classes, C1 and C2. So this is called decision boundary level. So the weights W1 to WP can be adjusted according to the error correction rule. Now, in order to solve the problem, in order to find the decision boundary, in order to find the correct equation for this line that can divide the patterns into two classes, class 1 and class 2, you could see in this equation, this is exactly depend on the values of W1 and W2. So Now you have to have the category to find the correct weights for W1 to WB, and in this respect we can use a correction rule. This rule is called the convergence algorithm in perceptron. First, consider the following changes in the transient signal diagram. This is the signal flow diagram. You can see in the signal flow diagram of a perceptron, this was the input, and in order to present the bias or threshold, you could show as x0, which is equals to -1, with the weight w0, which was equal to theta. So x1 with w1, x2 with w2, xp with wp, and the bias and the threshold is shown as x0, which is a constant input -1, and the weight, variable weight, is w0 or theta. So you have the input vector, you have the bias, and you have a variable weight. Adjusting the weight, updating the weights, or using a training algorithm, learning algorithm to find the stable weights, the final weights, to get the output. Which output? The output is calculated with respect to this transfer function, which is in the basic model, in the single layer perceptron, is a hard limit. The output could be -1 or +1. Therefore, we are finding this W1 and W2, which are the final weights, which are the stable weight, that you can divide the area into two classes simply. Therefore, the input vector, let's show the input vector as xn. We did have a -1, and this is the vector, which is shown x1 n, x2n, xpn transpose, and the weights, the vector weights, theta n, w1n, w2n. This n representing the values of each weight at instant n, or at iteration n, the first iteration. Original weights, you can set some original weights, and by defining some decision rule or learning rule, you can change the weights until we get a correct decision boundary that can solve the problem for us. And of course, we do need to calculate Vn, which is the multiplication of the Wn times xn. For the constant value of n, let's say at a given moment n, the equation w times x, which is equals to 0, represents the level equation, the separating equation, the decision equation that is plotted in the p coordinates. You can see in the p coordinates we have x1, x2 plane, and this is showing you the decision boundary. So this level divides the input space into two parts. When w times x is greater than 0, the input vector belongs to class C1, and if w times x is less than 0, or if it is -1, the input vector belongs to class C2. So it is doing a classification for you. It is dividing the input vectors into two classes, class C1 and class C2. Therefore, by having the two input vectors x1 and x2 that are linearly separate, this is very important. The basic model, the single layer perceptron, is working on this area. If these vectors are linearly separable, our problem is to find the weights vector w so that the condition 1 and 2, these two conditions, are fulfilled. So to find the vector w, If the input vector is correctly classified at the moment n, then no weight change in W will occur. We have a correct classification. So the new weights, which is Wn plus 1, which be equals to old weights, Wn. And if W times xn greater than or equals to 0, we can say xn belongs to class C1. And otherwise, this would be belonging to class C2. And now, if we don't have a correct classification. If these two are not equal, to find the new weights, we have the old weights minus the learning rate at moment n times xn. So this showing you xn belonging to class C2, and if you use the plus learning rate times eta times xn, and this would show you belonging to class C1. And this is very important to recognize that eta n is the learning rate parameter, and this learning rate parameters controls the amount of weight change at each stage. You see from one stage to another stage, from one moment to another moment, from one iteration to another iteration, we have some changes in weights. This is the change. This is the change in weights. Change in weight. It is controlled by the learning rate. You can see. So if this is positive, the rule is a constant, is increasingly constant, and we will now prove that the rule is convergent and that the number of perceptron is constant. So this is to show you that this learning rate must be a positive number, something between 0 to 1, and this has been proved, as you can follow the proof of showing that the learning rate must be positive small number. Originally, we would set some weights to 0 and having this equation, and if xn belongs to class C1, subdivision x1, and let's say the learning rate can be equals to 1. These are some summations. Therefore, finding Wn plus 1, which is Wn plus xn, and Wn plus 1 equals to x1 plus x2, x3, xn. Since it is assumed that the classes C1 and C2 are linearly divided, so there is always a solution such as W0, so it is called the adjusted weights. We now assume the smallest product to be the constant coefficient alpha. This is the smallest coefficient of this derivation, and by multiplying the two sides of equation 2 in W0, we have this equation you can see, and of course using the inequality Cauchy-Quartz, we would come to this equation, which I'm showing by the cross Wn plus 1, the norm of this, which is greater than or equals n square alpha square W square. We can obtain this amount another way, and coming up to the second equation, which is Wn plus 1, the distance which is less than n beta. Beta is the maximum of this. So we can conclude that the two equations for large value of n are contradictory unless we will obtain an equation in n has its maximum value. So the maximum value of these with respect to these that we have found, this is proving that the of course learning rate must be something between 0 to 1. And of course this is the criteria of efficiency of this the output dn, which is plus 1 if xn belongs to class C1, and minus 1 if xn belongs to class C2. And in the future chapters, we would define the cost function J as to calculate the amount of changes of weights with respect to the gradient descent of this equation, which we will go over it in chapter 4 and chapter 5. So this would conclude our chapter 4, and let's have some chapter 3, and let's have some more notes for these chapters. Single layer fed forward networks. As we said, this was by Rosenbeld for modeling visual perceptron. A fed forward of 3-layer unit. This is a fed forward. Of course, the single layer perceptron is a fed forward network, and this, as you can see, this is a fed forward network. And a simple perceptron structure, sine output node with threshold function, and input node with weights to classify input pattern into one of the two classes depending on whether output is 0 or 1. Example, input pattern x1 and x2. So let's show for this chapter 3, let's show one example. We have the inputs x1 and x2, two group of inputs pattern, see 0 0 0 1 1 0 minus 1 minus 1, and these are the weights, of course, the original weights, and can be separated by a line on the x1 x2 plane. X1 minus x2 equals to 2. Classification by a perceptron with W1 equals to 1. If you set W1 equals to 1 and W2 equals to minus 1 and threshold equals to 2. See, W1, let me show you the equation. It is very important to be able to solve these types of problems. You must solve these types of problems. As you could see, we did have a decision boundary. W1 x1 plus W2 x2 equals to threshold, With respect to this equation, we have an example. We have these four inputs 0 0 0 1 1 0 minus 1 minus 1, and two variables x1 and x2. The weights, see, with respect to this equation, x1 minus x2 equals to 2. You can say W1 equals to 1, W2 equals to minus 1, and threshold equals to 2. So this would be your decision boundary, decision equation, x1 minus x2 equals to 2. If you draw it in x1 x2 plane, you could see these dots, dark dots, are the inputs in class 1, and these would be in class 2. So to design this new network, this is your single layer neural network, single layer perceptron with two inputs x1 x2, weights plus 1 minus 1, hard limit transfer function, and f of x1 minus x2. And of course, this can classify these inputs 0 0 0 1 1 0 minus 1 minus 2 into two classes. You see, to two classes. Implement threshold. If you implement threshold by a node x0, now if you consider threshold, here we didn't consider threshold, now we want to consider the threshold. Constant output 1 for threshold, weight W0, a common practice in neural network design. This is the perceptron, single layer perceptron without the threshold. This is with the threshold. So perceptrons, linearly separability, a set of two the pattern x1, x2 of two classes is linearly separable if there exists a line on the x1, x2 plane, w0 plus w1, x1 plus w2, x2 equals to 0. Separates all patterns of one class from the other class. A perceptron can be built with three inputs. You can see x0 equals to 1, x1, x2 with weights w0, w1, and w2. N-dimensional patterns x1, x2, xp. Hyperplane, you do need hyperplane, w0 plus w1, x1 plus w2, x2 up to wn, xn equals to 0, dividing the space into two regions. Can we get the weights from a set of sample patterns? If the problem is linearly separable, then the answer is yes, by perceptron learning. So using perceptron learning, we can show a hyperplane to separate the input pattern into two classes. So let's see again some examples of linearly separable classes. For AND function, logical AND function, you could see this is the AND function. You can see we have four inputs. The inputs are x1, x2, minus 1, minus 1. And these are the weights. With respect to these weights, you can define this is the decision boundary equation, and this can be linearly separable. Therefore, the AND operation simply can be solved using a single layer perceptron. Same thing goes for logical OR function. You see, this is showing you how to solve the OR logical function using the single layer perceptron. Perceptron learning. What is the perceptron learning? The network input vector ij, including threshold input equals to 1, weight vectors is showing, and net equals to wij, which is the summation of wkik. Output bipolar should be minus 1 or 1 using the single node function. So the output is equals to 1 if this multiplication greater than 0, otherwise is equals to minus 1. The training samples, pairs ij, class ij, where class ij is the correct classification of ij, and the training update w so that all sample inputs are correctly classified. And if an input ij is misclassified by the correct weights, then we would say this is less than 0 and change the weights. So the learning algorithm for perceptron is to define the changes in weight going from one state to another state. So let's summarize this. Perceptron training algorithm. The algorithm for perceptron starts with randomly choosing weights, randomly choosing the initial weights, while some input vectors remain misclassified. Let ij be a misclassified input vector. Let xk equals to classes of ij times ij, implying that wk minus 1 times xk less than 0. Update the weights, see, using this learning rate, as I said. Incorrect and while, and should be, as I said, this learning rate should be a positive as a learning rate, and in justification to find the changes in weights, showing you to find new net move toward class ij. So this is showing you the perceptron learning. Perceptron learning convergence problem. Informal by problem that can be represented by a perceptron can be learned by the learning rule theorem if there is a W such that F of IP times W equals to class IP for all P training sample pattern IP class IP, then for any start weight vectors W0, the perceptron learning rule will converge to a weight vector W star such that for all P F of IP.WP, you have a correct classification. As you could see, finding these stable weights, the final weights, the adjusted weight, these would be called the adjusted weights. So let's have some notes. It is a supervised learning. So perceptron learning is a supervised learning. It means that you have to have the output available, and assuming that the problem is linearly separable, assuming the learning rate is a sufficiently small positive number, choice of learning rate. If the learning rate is too large, existing weights are overtaken, and if the learning rate is too smart, very close to zero, very slow convergence we do have. Commonly you can choose learning rate set to equals to 1 for single layer perceptron. And for non-numeric input, different encoding schema, color, for example, red, blue, green, yellow, you can set them to 0, 0, 1, 0 encoding. And for example, for green. Learning quality, generalization, it is very important notification, generalization, can be trained perceptron correctly classifying pattern not included in the training samples. Common problem for many neural network learning models. Depends on the quality of training sample selected. This is very important, how you select the training samples. Also, to some extent, depending on the learning rate, how you choose the learning rate. How can we know the learning rate is okay? Reserve a few samples for testing. This would be explained as an add line learning in future, and we will stop here up to this slide. This is the final slide for chapter 3. The rest of this file would be for chapter 4. So this would conclude our class notes. It would be an offline class for next Saturday, because we are still, we don't have an online class next Saturday. For next Saturday, this would be an offline class, and we will stop this. This is including whole chapter 3 for neural network course. Definitely go over these materials. I would provide some examples. You have to do those examples, and then we would give you again some homework problems as the second homework problems for chapter 2 and chapter 3. Have a good day, and we would have online class in coming weeks.